In this lecture, we will be covering the topic of vector projection. Recall, the dot product of two vectors A and B is the scalar defined by taking the components of each vector, multiplying the respective components, and adding those products. So A dot B is the product of the first components of A and B, plus the product of the second components of A and B, plus the product of the third components of A and B. And we also saw that another way to write the dot product is the length of A times the length of B times cosine of theta, where theta is the angle between A and B. And now we want to think about having two vectors, A and B, and we want to think about the idea of projecting A onto B. Pictorially, we can think of that as dropping a perpendicular from the tip of A down to B when the two vectors are end to end or beginning to beginning like this. And this is what we're after, this piece here. So we want to know what is the piece of this vector A in the direction of B. And if we define theta, as we mentioned here, where theta is the angle between A and B, we can actually think about what the length of this side here is. Let's say we call it L. So let's look at this triangle that we've just made. So we have a triangle where it's a right triangle. This side we're calling L. And the hypotenuse, the length of it, would be the magnitude of this vector A. And we have theta here. And we know from our SOHCAHTOA rule, we can get a relationship between these three quantities. Specifically, cosine of theta is adjacent over hypotenuse. And this L is what we're interested in. So this L is the magnitude of A times cosine of theta. That's the length of this piece we depicted here. And that is the magnitude of A when projected into the direction of B. Intuitively, a way you can think of this is if you shine a light straight down in a direction parallel to this perpendicular we dropped, it would be the shadow of A on this vector B. And this is what we define to be the scalar projection. So given vectors A and B, so these same vectors A and B, the scalar projection of A onto B, written in this way, comp sub B of A, we read that as the scalar component of A in the direction of B. And again, geometrically, we see that when we drop our perpendicular, the length of this side of this right triangle, we just argued it was the length of A times cosine of theta. But note, if we multiply both sides by the magnitude of B over the magnitude of B, we get this expression here. But now recognize that the numerator of that expression is the dot product of A and B. So we can write that scalar component of A in the direction of B as the dot product of A and B divided by the magnitude of B. So again, this is the magnitude of the projection of A onto B. And this will make more sense when we talk about the vector projection of A onto B. So if we look at our same picture, what we're now saying is, what is the component of A in the direction of B, but multiplied by a unit vector in the direction of V? So that we have here. This is the definition of the vector projection of the vector A onto the vector B. And it is nothing more than that scalar component directed in that direction of B. And so now our vector projection is this vector projection of A onto B. And we can plug in our formula for the scalar projection and get this formula here, A dot B over the magnitude of B squared times the vector B. So we can think of this as the vector component of A in the direction of B. You often see this, people who have physics background will have seen this sort of thing before. Oftentimes you have a force and you have to break it into horizontal and vertical components. Like in this next example. Suppose we have the vector W equals 7, 8. Let's find its scalar projection onto I, and remember, for a two-dimensional vector, I is the unit vector 1, 0. And then we want the vector projection of W onto I. So I can be depicted like this. And so we know this would be 1. And W would be this position vector of the point 7, 8. So our W will look like this. And we want to know what is the component of W in the direction of I. And we could probably guess the answer. The answer is going to be 7. And that's because the way that we define our vectors is that this 7 is associated with this I already. But we can see it work out in the formula. So let's first find the component of W in the direction of I from our formula. So we have W dot I, which is the vector 7, 8, dot product, the vector 1, 0, divided by the length of I. Doing this dot product, we have 7 times 1 is 7, plus 8 times 0, which is 0, and the length of I, it's a unit vector, is 1. So we get 7, which is what we expected. And to depict that, if we drop that perpendicular down, and again, think of it as shining a flashlight or the sun directly above, and this is the length of this line segment here, the bottom of this triangle, is the shadow that W casts on the vector on the vector I. If we want the vector projection, then we take this answer here, the component of W in the direction of I, times I over its magnitude, but again, I is a unit vector. So we get 7I, or the vector 7, 0, which would be the vector here. And so that vector is the vector projection of W onto I. Let's look at another type of question because we don't necessarily have to project onto these unit vectors, I or j or k. We may want to project, say, w onto v. In this problem, we're asked to write w as the sum of a vector parallel to v and a vector perpendicular to v. And so we're going to do this by saying w will equal, we'll call it w parallel plus w perpendicular, or w perp. To draw these, we see w will be the position vector of the point 1, 2, 4. So w can be thought of pointing from the origin to this point 1, 2, 4. And then we depict v as the position vector of the point -1, 2, 3. So we have -1, 2, 3. And so we have this point here. And so our vector v would point from the origin to that point -1, 2, 3. And we now want to think about projecting. First step will be to project w onto v. And the reason for that is to find w parallel. Well, the projection of w onto v, the vector projection of w onto v, is by definition parallel to v. It's a vector in the same direction. So we are going to geometrically do this idea of dropping a perpendicular down here, and the resulting vector we will call w parallel, and that again will be the vector projection of w onto v. So w parallel is the scalar component of w in the direction of v times unit vector in the direction of v. And recall that scalar projection is w dot v over the length of v or w dot v over the length of v squared times the vector v. And we can figure out what this value is here. W dot v, we see from the definitions of w and v, we can do the dot product. 1 times -1 plus 2 times 2 plus 4 times 3 all over the length of v squared. The length of v, we know, is the square root of, we square these entries and add them, -1 squared plus 2 squared plus 3 squared, but we're squaring that length. And then we multiply this by the vector v. So this becomes -1 plus 4 plus 12, all divided by, here we have 1 plus 4 plus 9 times v, or here we have 15 in the numerator, and in the denominator we have 14. So the vector projection of w in the direction of v is 15/14 times v, which actually makes sense from the picture. You can see that this purple vector, we had to make v a little bit longer to get the vector projection of w in the direction of v. By a little bit longer, we mean exactly 1/14 longer. So this gives us part of the answer. This gives us w parallel. But now we also want this w perpendicular. But here's the catch, is that we know what's known. We just found w parallel, and we were given w. So w perp we can solve for. So w perp is equal to w minus w parallel that we just solved for, or w, which is 124, minus w parallel, which is 15/14 times v, which was minus 1, 2, 3. And if we solve for that, and we work out the math, this will be our answer. So here is our w parallel, and here is our w perp. And again, to get this w perp, that is nothing more than computing this difference that we set up here. And the way this works out is we can now depict w perp, and it will look like this. And if you recall the triangle law for addition for vectors, we can actually see that that vector w can be depicted as the sum of this w parallel and w perp. And so this is a very common type of question, to take a vector, in this case w, and write it as the sum of a vector parallel to this given vector v and a vector perpendicular to it. And this type of problem really helps depict what we're doing when we actually do vector projections.